How were the Great Pyramids really built? Were they the work of thousands of laborers with ropes and ramps, or was something far more mysterious at play? For centuries, scholars and explorers have struggled to explain their impossible precision. Ancient texts hint at secrets long buried. Stones weighing tons appear to defy gravity itself. As we uncover two shocking theories, one rooted in forgotten engineering, the other in the unthinkable, you will see why the pyramids remain the greatest mystery of all. Stay until the final chapter, where the most disturbing possibility is revealed. But before we dive in, let me know if you're enjoying this kind of long, gentle history. Feel free to tap that like button and subscribe, only if you truly love what I'm doing here. And in the comments, share where you're tuning in from and what time it is in your city. I always love seeing our little bedtime crew gathering from every corner of the world. Now lower your lights, maybe let a soft fan hum in the background, and settle in. Let's ease into tonight's quiet journey together. Chapter 1: The Mystery That Defies Time. Dawn spills over the desert and the Great Pyramid rises like an answer to an unasked question. Light slides across its faces, folding gold into shade and revealing edges cut with unforgiving care. The air smells of sand and old labor, and the river glints like a seam of light beyond the stones. A solitary jackal moves along a ruined path, pausing where modern footfalls feel recent beside eternal rock. Visitors stop at the base and lower their voices as if the monument will overhear them. The pyramid remains both an engineering triumph and a deliberate silence, a proof and a riddle. Measuring ropes and imagined ramps seem inadequate against the precision carved into every joint and corner. At dawn, the structure demands more than admiration. It demands explanation and then more questions. It feels ancient and modern at once. The scale defies immediate comprehension. Shadows sharpen the geometry further. Silence deepens around each corner. A hush like expectation hangs. Sight cannot fully hold its measure. Time seems to curve here. Breath catches at the stonework. Questions crowd the mind. Scholars have offered explanations that sound plausible when written but feel thin when held against stone. Ramps of earth and timber, thousands of workers hauling sleds, clever levers and brute force form the familiar story. Archaeologists point to villages of laborers, tools of copper and stone, and records carved in mud and paint. These discoveries are real and important, and they anchor the past in human hands and sweat. Yet when the numbers are crunched, the neat solutions fray at the edges, and the math begins to resist easy closure. The weight of each block, the tolerance of joints, the length of ramps needed, these details accumulate into a cliff of improbability. Enthusiasts imagine endless lines of men hauling, but images do not replace calculations and physical feasibility. Modern experiments reproduce some feats, yet they never quite capture the sustained precision or the speed implied by construction timelines. It feels ancient and modern at once. The scale defies immediate comprehension. Shadows sharpen the geometry further. Silence deepens around each corner. A hush like expectation hangs. Sight cannot fully hold its measure. Time seems to curve here. A long debate has grown around the pyramid like a ring of shadow that refuses to yield. On one side stand the champions of manpower and method, convinced that human ingenuity and organized labor suffice. They point to burial chambers, workforce bones, and administrative records that speak of provisioning and planning. On the other side are those who sense a gap between explanation and phenomenon and suspect hidden factors. These skeptics ask hard questions about quarrying seams, transporting massive stones over distances, and lowering blocks into place with centimeter accuracy. The discussion shifts between laboratory measurements, field excavations, and speculative reconstruction, and it rarely reaches consensus. Both camps use evidence, but they shape it under different lights and arrive at different urgencies. The real conflict is not only technical, it is philosophical, about what counts as an explanation and how far we grant the ancients' modern methods. It feels ancient and modern at once. The scale defies immediate comprehension. Shadows sharpen the geometry further. Silence deepens around each corner. To set the stage for what follows, imagine two paths that split from this central dilemma. One path seeks lost ingenuity, machines and methods erased by time but hinted at in traces and tools. The other looks for principles that seem to us like magic, forces of nature harnessed deliberately and then forgotten. Both roads have promise and peril, and both demand that we re-examine assumptions long held as settled. This narrative will follow both paths, allowing each to deepen until you can judge which seems more likely or more unsettling. The first theory will ask whether advanced mechanical thinking, perhaps even devices unknown today, lay behind the work. The second will ask whether a manipulation of resonance and vibration could have made stones obey commands. Before we test either theory, the puzzle must be laid bare. Here are the facts that push us towards strange explanations. It feels ancient and modern at once. The scale defies immediate comprehension. Shadows sharpen the geometry further. First, consider the raw measurements that make the pyramid so unnerving to engineers and historians alike. The Great Pyramid aligns almost perfectly to cardinal points, and its base forms a near-perfect square over 400 feet per side. The block's display faces smoothed and joints fit so tightly that even a knife blade cannot slide between many of them. Some interior passages intersect at angles so precise that modern surveyors blush with admiration and curiosity. The scale of the labor implied by such accuracy challenges the tools attributed to the period, and the logistics grow daunting. Quarrying methods known from remains yield chisel marks and drill holes, but not an answer to how some cuts achieved such uniformity. When modern stonecutters attempt replicas, they meet costs in time and method that the known Egyptian economy would have struggled to sustain. This mismatch between observed outcome and reconstructed input lingers like a bruise on the accepted narrative. It feels ancient and modern at once. The scale defies immediate comprehension. Further anomalies appear when transportation is examined with care and not with romanticized imagery. Rivers can carry heavy loads, but the quarries for some casing stones lie on terrain that would make simple barges impractical. Tracks of ancient roads are scarce and often interrupted by geological features that complicate straightforward hauling. Even sled experiments that succeed in short trials demand maintenance, time, and a workforce that multiplies costs rapidly. To move tens of thousands of blocks in the purported time frame requires an efficiency that the archaeological record only partially supports. Supply chains, food, shelter, and the sheer coordination of skilled labor would have to be astonishingly well organized. Written records about such logistics are fragmentary or non-committal, leaving gaps that invite more creative hypotheses. When the standard model resorts to project management as the main explanation, it begs the question of how that management achieved near impossible results. It feels ancient and modern at once. The second set of facts that trouble scholars involves internal precision and alignment with the heavens. The pyramid acts as a giant observatory in many ways, with shafts and chambers aligned to stars and celestial events. Ancient builders seem to understand cycles of the sky with a depth that equals later astronomers, and they encoded knowledge in stone. This astronomical mastery suggests a culture that combined ritual, science, and meticulous measurement in ways modern researchers are only beginning to grasp. But ritual alone cannot explain the physical mastery over stones that the building demonstrates. The relationship between astronomical intention and architectural execution is intimate, indicating that builders worked to exacting standards with repeated calibrations. How did they translate celestial measurements into blocks, grades, and junctions on the ground with such consistency? Answers to this question tip the scale toward techniques that bridge observational knowledge and mechanical application. Feels ancient and modern at once. The human story behind the stones complicates the puzzle further and deepens the emotional stakes of our inquiry. Evidence of worker camps suggests skilled teams with seasonal labor patterns rather than disposable slave hordes, and this implies training and expertise. Artisans and quarrymen left marks of pride and ownership, inscriptions that speak of titles and crews, not anonymous mass labor. The presence of organized medical remains, bakeries, and housing shows an administration capable of sustaining large projects over decades. Administration is not mystery, but the administrative records seldom detail the specific technical methods used to place the heaviest stones. Instead, the records dwell on logistics, provisioning, and royal ritual, as if the means of moving stones were mundane or deliberately unrecorded. This selective account deepens suspicion that crucial knowledge might have been withheld from common record, perhaps preserved only within closed guilds. Thus, the social evidence invites the idea that what we lack in the record was known to a few and guarded carefully. Feels ancient and modern at once. As our story widens, tensions between observed craft and documented practice inflame curiosity and invite bold thought. Some researchers propose that lost machines, cranes, counterweight systems, and ingenious pulleys once complemented human muscle. Others speculate about temporary structures that distributed weight and allowed stones to be moved with mechanical advantage. These ideas translate the problem into a question of lost technology rather than impossible will, and they have experimental promise. Reconstructors have built models and partial systems that show how clever leverage could reduce required human power significantly. Yet critics point out the lack of durable remains of such devices, and the corrosive effects of time on wood and rope make archaeological traces rare. Still, the hypothesis cannot be dismissed purely for lack of material remains, because absence of evidence is not evidence of absence. Feels ancient and modern at once. Another radical direction of thought asks whether the ancients harnessed principles that look like magic to us, such as resonance, buoyancy, or material alteration. Legends and later accounts sometimes speak in metaphor about songs or chants that moved objects, and while myth is slippery, it often preserves kernels of method. Laboratory tests show that vibration and resonance can produce surprising effects in controlled settings, making objects vibrate, shift, or even float in rare circumstances. If the builders discovered ways to change friction or cohesion between block and ground temporarily, they could have manipulated stones with far less brute force. This line of thinking demands careful skepticism, but it also offers experimental pathways that modern scientists can test with rigor. Whether these were practical engineering techniques or symbolic descriptions of more mundane methods remains an open and tantalizing question. Feels ancient and modern at once. Our narrative must also reckon with the possibility that multiple methods overlapped, combining human labor with clever devices and subtle physical knowledge. Ancient craftsmen could have used a mosaic of techniques, adapting solutions to specific problems rather than relying on a single grand method. This hybrid model makes practical sense. Use manpower where possible, machines where helpful, and clever physical tricks where expedient. Such a composite would explain why some elements of the pyramid map cleanly onto known practices while others stubbornly resist replication. It would also fit the social picture of specialized guilds passing guarded techniques to apprentices, preserving secrets in ritual and practice. Histories that seek one single cause often fail to see the interplay of many modestly ingenious choices summed into greatness. Therefore, before accepting or discarding either of the forthcoming theories, imagine them as compatible complements rather than mutual exclusives. Feels ancient and modern at once. Finally, stand once more at the base as the sun climbs and shadows retreat to reveal the full face of the structure. The pyramid resists explanation with a patience that teaches humility to every theory that approaches it with certainty. Our inquiry will move methodically into two bold hypotheses. One that locates genius in mechanical invention and another that seeks power in waves and vibration. Each theory will be tested against archaeology, engineering, experiment, and imagination so that you can weigh plausibility and unease. Do not expect simple resolution. Complex mysteries seldom yield to a single tidy answer, and the past often keeps its confidences. But as we proceed, keep in mind that doubt is not defeat. It is the engine of closer study and braver reconstruction. Stay with this journey to the end, for the second theory in particular will challenge what you believe possible and may reshape how you see history itself. Prepare to be unsettled, to learn, and to reconsider what ingenuity can mean across the ages. Chapter 2: The Accepted Story We Were Told. Morning on the plateau brings a clatter of voices, the scrape of wooden sleds, and the measured rhythm of human labor. In the familiar story, the Great Pyramid rose through organized toil, meticulous planning, and applied engineering. Workers hauled dressed blocks across sand, tied cords to timbers, and moved stones with coordinated pulls. Ramps of packed earth or timber reportedly permitted upward progress, while teams levered blocks into place and finished surfaces with copper tools. This image explains the monument in human terms and comforts a modern mind that prefers agency over miracle. It places architects, foremen, and skilled artisans at the center of a vast supply chain and logistic feat that connected quarries, work camps, and the royal court. Measured in the archaeological record, this narrative aligns with discoveries of bakeries, barracks, and tool marks, and those finds create a scaffolding of plausibility that is hard to dismiss. Yet the fuller truth proves more complex and invites deeper scrutiny. Archaeological digs have revealed surprising domestic detail that supports the human labor account and gives it texture. Near the plateau, excavators uncovered remains of organized work camps, bakeries with huge ovens, rows of dormitory-style housing, and butchered animal bones that point to large-scale provisioning systems. Graffiti and inscriptions identify work crews and foremen, connecting men to specific tasks and creating a social map of construction labor. Tools found in situ include copper chisels, dolerite pounders, wooden sled fragments, and rope impressions, each serving as a physical testimony to hands-on craftsmanship. Pottery shards and ostraca with lists of rations underscore administrative oversight and suggest seasonal labor cycles aligned with the Nile flood. These discoveries move the pyramid story away from myth and toward human biography, offering a narrative of people, routines, and bureaucratic control that feels concrete and credible. Together, these artifacts portray an economy mobilized for building, where skilled artisans worked alongside support staff in coordinated campaigns across many seasons. The mainstream reconstruction builds a coherent economic and organizational picture that makes engineering sense at first glance. Scholars propose various ramp configurations to solve the elevation problem, from long straight ramps extending across hundreds of meters to spiral ramps that hugged the pyramid as it grew higher. Each proposal brings specific advantages and costs, and engineers model traction, friction, and required workforce sizes to determine feasibility. The ramp becomes a central hypothesis, a temporary structure that shifts the puzzle toward logistics and materials management rather than mysterious forces. Under this scheme, the workplace becomes a choreography of teams, signals, and stages, with specialized crews for quarrying, dressing stones, hauling, and finishing. Administrative records interpreted by historians show quota systems, redistribution of food, and seasonal labor cycles that could have matched construction demands over decades of steady work. This reconstruction comforts those who see the pyramids as grand but ultimately human products of social organization, administrative reach, and practical engineering precisely. When the ramp hypothesis is pressed into fine detail, uncomfortable questions begin to mount and the neat picture fractures at the edges. Ramps of the size necessary to move the heaviest casing stones would themselves have required stupendous amounts of material and labor to build, maintain, and then dismantle. The volume of fill for a straight ramp reaching the upper courses would rival that of the pyramid itself, creating a logistical circularity that invites skepticism. Archaeological traces of such vast temporary structures are minimal and contested, and while erosion and reuse of materials might erase evidence, the near absence of reliably identifiable ramp remains troubles researchers. Alternative ramp models reduce materials but introduce operational complexities, such as sharply angled turns or precarious loading points that increase risk and require more sophisticated engineering than the simplest story admits. These problems open a gap between a plausible concept and a fully demonstrated method that satisfies both field evidence and mechanical calculations persistently. Beyond ramp volume, mathematical and geometrical issues further complicate the accepted account and demand careful reckoning. The interior passages and chambers feature angles and tolerances that imply repeated measurement and exceptional control over orientation, leveling, and perpendicularity across large distances. Some joints are fitted with millimeter-level precision, and some casing stones present faces so planed that modern masons marvel at the finish achievable with copper tools and dolerite pounding stones. When engineers model the workflows required to place such elements, they find narrow margins for error and timelines that press ancient labor systems to extreme efficiency. Placement of heavy blocks in confined corridors, where scaffolding is limited and leverage compromised, suggests techniques beyond crude hauling, and these operations would have required staging, counterbalancing, and careful sequencing. Some researchers therefore explore mechanical aids and experimental reconstructions. Transport logistics present their own knot of difficulties that complicate confident explanations and enlarge the mystery. While the Nile offered a crucial artery for moving heavy stone, seasonal constraints and the requirements of timing posed operational difficulties that could not be ignored. quarries for some of the most prized blocks sat in places where overland transfer to the river was arduous, and the existence of engineered canals or sled ramps to navigate these gaps is debated. Claims that barges simply carried every block loss over navigational hazards, the energy cost of loading and unloading, and the careful timing needed to align flood seasons with construction schedules. Overland hauling across uneven terrain would have demanded durable roads or continuous trackways, yet clear traces of such permanent routes remain limited and fragmentary, which raises questions about throughput and efficiency. Faced with these logistical challenges, many researchers admit that transport remains one of the most problematic aspects of the conventional model and debate. Curiously, the documentary record speaks in administrative terms more often than in technical detail, and that selective voice deepens the puzzle. Lists of rations and labor quotas, inventories of raw materials, and ritual texts saturate temple archives. Yet explicit instructions for moving multi-ton stones are scarce or oblique. This imbalance suggests either that the techniques were so ordinary they needed no inscription, or that they were protected as specialized knowledge withheld from public record. Guild secrecy, ritual initiation, and apprenticeship could have preserved mechanical practices within closed circles, leaving little to archaeological visibility beyond occasional tool marks and indirect references. Or perhaps scribes recorded success in terms of royal honor and religious duty rather than practical manuals, making logistics legible but specific methods opaque. Whatever the reason, the absence of straightforward technical manuals nudges inquiry toward hypotheses that seek lost or deliberately hidden techniques, and it invites experimental work to restore the missing chapters. Some view it as a clue. Experimental archaeology has offered partial vindication for traditional models but has not delivered a full resolution to the construction problem. Teams have reconstructed ramps, sledges, and hauling techniques and demonstrated that, with careful coordination and favorable conditions, blocks can be moved and lifted. Such projects prove that human muscle combined with clever tools can accomplish remarkable things, and they provide valuable calibration for theoretical models. Yet scaling these experiments from dozens of trial blocks to tens of thousands in a sustained program changes the problem in kind, exposing issues of wear, supply, and cumulative error that single demonstrations cannot capture. Recreation projects also depend on modern safety standards, volunteers, and controlled conditions, which differ from seasonal labor pools subjected to environmental stress and political imperatives in the Old Kingdom. These experiments remain crucial but cannot substitute for missing archaeological data. Public imagination prefers tidy narratives, and the story of ramps and human effort fits that demand neatly, which complicates scholarly debate. Television documentaries and school textbooks favor visuals of long lines of workers and sweeping ramp reconstructions because they explain complex feats in familiar human terms. This accessibility promotes a comforting narrative in which social organization and administrative power scale up to monumental achievement. Yet appealing stories risk silencing anomalies and reduce incentive to pursue more awkward or speculative lines of inquiry that might unsettle neat morals about progress. When audiences accept a single image as complete explanation, exploratory research may meet less appetite for funding and less public support, and that cultural inertia can slow methodological innovation. Historians must therefore balance narrative clarity with stubborn attention to inconsistencies and gaps in evidence at all costs. To bridge the divide between plausibility and anomaly, many scholars propose hybrid models that combine conventional labor with mechanical cunning and staged innovation. Suggestions include counterweight systems that used simple mechanical advantage to reduce human loads, movable short ramps that were advanced incrementally, and temporary scaffolding that permitted precise manipulation of heavy elements. Some reconstructions imagine teams using levers and fulcrums in staged sequences, so that heavy stones are never moved more than a few meters at a time before being repositioned and adjusted. Such approaches reduce the need for singular grand ramps and emphasize adaptability, allowing builders to tailor methods to local conditions and to learn and refine techniques as they progressed. These mixed models also accommodate the social record of skilled specialists who might have operated and guarded particular mechanical know-how while general labor supported the effort. Hybrid explanations preserve human agency while leaving room for clever lost engineering that time has mostly effaced from the visible record. The debate over construction methods carries interpretive stakes that reach beyond mere engineering and into how we imagine ancient intelligence and social organization. If the pyramid is fully explicable by known techniques, it confirms narratives of administrative brilliance, coordinated labor, and incremental technological progress in early complex societies. If instead gaps persist that point toward forgotten machines or unusual physical manipulations, then the past appears more inventive, adaptive, or even mysterious in ways that challenge linear models of progress. Our preference for one conclusion over another can reflect modern anxieties about obsolescence, genius, and the security of knowledge, and these biases shape how evidence is framed and interpreted. Scholars, therefore, must be attentive to the cultural lens they bring, testing hypotheses with quantitative models and material experiments while remaining open to disruptive possibilities. How we read the stones tells us as much about our own time as about the builders who first raised them, and that double mirror complicates certainty. At the close of this conventional account, the question lingers like sand in a boot. If ramps, sleds, and massive human organization do not fully account for the pyramid's finer mysteries, then what did the builders do differently? Having laid out the strengths and the real limits of the accepted story, we are poised to examine sharper hypotheses that reach beyond routine explanations. In the next chapters, we will explore one dramatic possibility that ancient Egyptians employed mechanical systems lost to us now, devices that conferred leverage and precision beyond what unassisted labor could achieve. We will also explore a second possibility that sounds more like myth but has physical analogs in resonance and vibration, techniques that might alter friction or lift in surprising ways. Both theories will be measured against evidence, experiment, and plausibility, and both raise disquieting implications for how much technological knowledge can be forgotten. The mystery widens. The next chapter pries open the ancients' toolbox soon. Chapter 3, Theory 1, The Lost Machines of Ancient Egypt. When the neat story of ramps and sleds begins to fray, a suggestion rises at the edges of scholarship, an idea that shifts the center of gravity from pure manpower to mechanical advantage. Picture behind the mastaba's workshop a system of wooden gantries and winches, ropes feeding over groove drums, counterweights balanced to lift with predictable economy. This is not a fanciful impulse, but an interpretive move based on fragments and engineering logic. If builders mastered simple machines and combined them into compound systems, the heavy lifting problems diminish and precision grows. The discovery of well-cut mortise joints, carefully bored dowel holes, and traces of fitted timbers argues for carpentry used in structural and mechanical contexts. In that world, the mason operates from a stable, adjustable scaffold, and the block is never left to brute force alone. The possibility demands careful study, and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. The culture's broader material achievements make devices plausible rather than outlandish, because Egyptian craft displays attention to fit, finish, and joined construction across media. Boats required precise joinery and pinning. Furniture shows careful mortising and tenons, and ritual objects reveal exacting control of metal and wood. These skills translate to mechanisms where controlled motion matters. Even with bronze and copper tools, artisans could fashion pulleys, axles, and guiding frames that reduce friction and control direction. Textiles and ropes with known tensile strength could serve as drives, and seasoned timber could form bearing surfaces. Once systems of mechanical advantage existed, they could be scaled and adapted to local demands, evolving into specialized gear for quarrying, hauling, and final setting. Such an evolving workshop culture would support guilds' guarding methods, and those groups might leave administrative notes while avoiding technical disclosure. This possibility demands careful study, and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Reconstructive thinking proposes concrete devices that could fit available materials and known skills without invoking modern metallurgy. Counterweight lifts provide one model, transforming potential energy into a controlled vertical force while minimizing manpower. A balanced shaft or pit could accept heavy stones and, through a system of ropes and simple pulleys, permit steady lowering or raising. Gantry frames placed on temporary platforms would stabilize loads and allow lateral placement with fine adjustments. Portable cranes with wooden booms and guy lines might explain how facing stones were set with care, while sliding jibs and cribbing could permit incremental elevation without massive straight ramps. These ideas reduce logistical volumes and concentrate effort on durable temporary structures rather than on earth moving at grand scale. The possibility demands careful study, and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Archaeology yields suggestive but fragmentary support for mechanical systems when indicators are read with engineering eyes. Mortise sockets in stone and wood, repetitive drilled holes in strategic positions, and patterns of where near voids can imply mounting for pivots or bearings. Paired slot marks and board impressions hint at planks or runners that stabilized heavy loads. Corroded metal fragments found near quarries could be fasteners once part of composite fittings. Even the distribution of tool marks on quarried faces sometimes reflects controlled rotation or staged dressing consistent with clamping jigs. These traces rarely prove a specific device on their own, but taken as a suite, they indicate a workshop logic attentive to repeatability and control. The possibility demands careful study, and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. When experimental teams attempt to recreate hypothesized devices, the results can be illuminating and sobering at once. Wooden cranes and gantries built from native timbers have demonstrated staged lifts, and counterweight experiments show how human teams can orchestrate heavy movements with predictable force. Jibs and rocking frames allow small adjustments that lead to accurate placement. However, these reconstructions also reveal limits. Wood succumbs to wear, rope stretches, and joints loosen with repeated cycles, demanding maintenance regimes that leave little archaeological trace. Scaling from a dozen test blocks to tens of thousands alters the problem in scope and introduces consumption rates of timber and rope that require logistic frameworks. Still, experiments illustrate that clever mechanics materially reduce manpower needs and increase placement precision. and they invite further field trials under conditions closer to historical realities. The possibility demands careful study and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Social dynamics pivot when machines enter the story because control over gear creates social stratification and secrecy. If certain crews operated complex mechanical systems, they gained specialized authority and resources, and their expertise might be transmitted within restricted workshops through apprenticeship, ritual, and oath. The documentary records focus on rations and quotas would then reflect provisioning of these elite crews rather than detailed manuals that could disseminate mechanical knowledge. Secrecy could explain the sparse direct description of techniques in surviving inscriptions. Technical know-how stayed practical and embodied rather than textualized. Meanwhile, the visible labor force performed strenuous hauling while the machine teams orchestrated lifts at critical moments. This arrangement preserves the image of organized manpower while embedding critical mechanical steps in guarded practice. The possibility demands careful study and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Comparative archaeology supplies further plausibility by pointing to contemporaneous cultures with mechanical concepts and devices that might travel through trade and exchange. The Near East shows early development of simple lever and pulley ideas, and later classical authors describe crane-like devices in construction contexts. Knowledge moves with merchants, captives, and itinerant craftsmen, and the exchange of mechanical concepts could predate explicit textual evidence. If Mediterranean and Levantine contacts transmitted ideas about bearing surfaces, pinning, and counterweights, Egyptian builders might adapt and refine those notions within local material constraints. Cross-cultural diffusion does not explain everything but widens the pool of feasible solutions and suggests that mechanical thinking could emerge from a web of interactions rather than sudden isolated invention. The possibility demands careful study and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Material constraints complicate and shape any lost machine account. For the availability of suitable timber, durable rope, and reliable metal fasteners limits possible device lifespans and complexity. Egypt lacked abundant hardwoods locally, relying on imports for particularly strong timbers, and that scarcity would channel design toward reusability and modular parts recoverable after use. Rope technology matters because stretching, wear, and splicing determine load limits and maintenance cycles. Metal fasteners, while available in limited forms, corroded and left ambiguous traces. Designs that minimized vulnerable parts or permitted rapid replacement would be favored, and that engineering optimization could obscure evidence further by reducing the archaeological fingerprint of machines. Understanding resource flows becomes central to modeling what devices are feasible and sustainable. The possibility demands careful study and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Resistance to the lost machine idea comes from reasonable caution and a demand for parsimony. Yet the hypothesis also provokes valuable new research directions. Skeptics argue that until a clear mechanical artifact appears, the claim remains speculative, and they insist that known labor organization suffices. That admonition promotes rigorous standards and keeps imaginings tethered to material proof. At the same time, the lost machine hypothesis stimulates targeted fieldwork looking for mounting sockets, patterning of wear, and worksite debris that previous researchers might have overlooked. It also encourages more ambitious experiments that test durability and throughput over extended cycles, reflecting realistic seasonal campaigns. The intellectual tension between caution and creative reconstruction enriches the debate and accelerates methodical study rather than idle speculation. The possibility demands careful study, and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Some proponents push the idea further, imagining modular scaffolding and compound mechanical arrays that appear almost modern in sophistication yet constructed from ancient materials and geometric insight. These speculative reconstructions propose sequences in which stones are moved a few meters at a time, jacked, clamped, and shifted with mechanical advantage, eliminating the need for enormous ramps and distributing effort across time and technique. Compound systems of sliding platforms and pivoted arms could permit controlled orientation and indexing of blocks to achieve the observed precision. Such designs remain speculative because they rely on inferred components and absent hardware, but they serve as useful thought experiments that translate archaeological ambiguity into testable engineering scenarios. The possibility demands careful study, and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. At the chapter's end, the lost machine theory stands as a compelling alternative to brute force narratives, yet remains incomplete and contested. It explains many anomalies by relocating ingenuity to mechanical practice, fills gaps in placement precision, and aligns with evidence for skilled carpentry and administration. It also forces attention to resource logistics, maintenance cycles, and social control over knowledge. Critics rightly call for more decisive artifacts and clearer archaeological markers, and proponents answer with experimental reconstructions and targeted searches for mounting traces. The debate is productive because it turns absence into a research program and technical imagination into concrete experiments. As we move to the next chapter, prepare to meet a different kind of shock, one that asks whether the ancients might have harnessed forces that feel more like ritual and physics than like timber and rope. This possibility demands careful study, and rigorous experimentation are required to confirm or refute this hypothesis in field and laboratory settings. Indeed, more work must follow to clarify details. Chapter 4: Signs of Advanced Engineering Beyond Their Age. At close range, the pyramid stonework speaks in a language of near imperceptible tolerances. It is not merely that blocks are large. Many faces are planed so flat and joined so tightly that light does not pass between them. The casing stones once formed a gleaming coat, each unit correlating with its neighbors in planes and seams that align across great distances. Interior passages show cuts and junctions that maintain angles to astonishing exactness over lengths that would challenge modern quarry teams. These attributes suggest measurement regimes and cutting techniques that focused on repeatable outcomes. When engineers study the joints and surfaces, they note operations consistent with clamping, jigs, and measured indexing rather than ad hoc dressing alone. The result is a set of physical features that look engineered, not accidental, implying techniques that aim for fine tolerance repeatedly and at scale. Such workmanship invites further inquiry. These features force engineers to rethink assumptions about tools, process, and skill levels today. The geometry of the structure betrays an understanding of alignment and orientation that goes beyond local practicality. Surveyors have long marveled at how closely the Great Pyramid conforms to true north, with deviations measured in minutes of arc. The base forms a remarkably regular square, and the faces incline to precise angles that yield an apex aligned with intended proportions. Achieving that level of orientation requires reliable reference systems and repeated calibration during construction phases separated by time. Such calibration could be effected through celestial observations, sighting devices, or the controlled use of measuring fixtures embedded in the construction process. Whatever the means, the builders produced repeatable geometric outcomes across hundreds of meters, a fact that pushes the limits of what a purely ad hoc effort could sustain. To achieve such orientation, they likely used repeated stellar observations, fixed sighting posts, measured chords, and transferable benchmarks maintained across the site by specialized teams overseeing alignment. Consider also the internal architecture, where chambers and corridors intersect with minimal deviation. The Grand Gallery and King's Chamber alignments suggest staged operations where blocks were not only moved but placed with attention to internal datum points. These interior spaces required solutions for temporary support, controlled lowering, and sealing that preserved intended angles and surfaces. The corbelled ceilings and relieving structures above chambers indicate an understanding of load distribution and the need to protect internal voids from compressive forces. Executing these features without damaging adjacent masonry demands mechanical control over movement and pressure during construction phases. The evidence therefore hints at engineering protocols embedded in practice. Interior datum points, temporary bearing frames, and sequential measurement protocols could have managed cumulative error, replicating orientation across successive courses, while craftsmen applied corrective adjustments based on trial fittings and reference marks. When modern engineers attempt to recreate precision at scale, they confront challenges that mirror ancient puzzles. Cutting stone to tight tolerances across many pieces requires stable fixtures, effective measurement transfer, and quality control procedures to prevent cumulative error. In workshops today, machinists rely on jigs, gauges, and calibrated tools to reproduce shapes with consistency. Ancient builders would face the same error propagation problems if they attempted comparable repetition without such systems. Similarly, lifting and placing heavy elements safely and accurately in constrained spaces requires staged mechanisms that limit uncontrolled motion. These analogies do not prove ancient machines existed, but they show why similar mechanical concepts would be natural responses to observed construction demands. The parallels encourage searching for physical traces of such systems. Those practical parallels compel archaeologists to seek physical remnants of jigs and gauges, and to test whether index measurements could be preserved through simple but robust fixtures that a team could redeploy across multiple building seasons. Archaeological indicators that support mechanical interpretations appear in subtle patterns rather than in grand artifacts. Repeated sets of holes and sockets carved into bedrock and blocks can serve as mounting points for temporary frameworks, where patterns on stone surfaces adjacent to passages suggest repeated contact with wooden runners or bearing components. Found timbers and rope fragments, though rare, reveal woodworking and cordage skills compatible with pulley and hoist systems. Fragmentary fasteners and metal remains near quarry sites, when analyzed, show use in composite assemblies rather than ornamental contexts. These scattered clues cohere into a picture of workshops producing specialized fixtures and temporary machines adapted to repetitive tasks rather than one-off improvisations. Taken together, these signs form a network of indirect evidence that, while individually inconclusive, collectively imply systems of control used repeatedly to secure predictable results amid large-scale movements and placements of stone. The presence of specialist labor adds another element to the argument for lost machines, because complex gears and counterweight arrays would demand trained operators and maintenance crews. Evidence from worker settlements points to units with specific skills: stonemasons, carpenters, rope makers, and logisticians, who could combine in teams to operate machinery and manage supply lines for timber and tools. If certain stages of construction depended on mechanical rigs, those rigs would require skilled stewardship to prevent catastrophic failures. The social structure inferred from the archaeological record supports the existence of such specialist roles and encourages the hypothesis that some tasks were intentionally sequestered within expert crews whose knowledge was guarded. Institutional secrecy could explain gaps. Skilled operators would also record practices in embodied routines and workshop lore rather than in public texts, and that mode of transmission favors practical rehearsal over written manuals, which leaves fewer traces for modern discovery. Material economy frames what machines could have looked like and how long they could last in repeated use. Timber scarcity, for instance, influences design toward reusability and modular components, while rope technology sets limits on sustainable loads and defines maintenance cycles. These constraints push designers toward mechanical advantage that minimizes vulnerable parts, preferring solutions that use counterweights, pivoted frames, and short-range jacking over extended lever systems that demand massive timbers. Such design choices reduce archaeological footprints and make artifacts less obvious after centuries. Understanding resource flows and maintenance regimes thus becomes essential when we model plausible ancient machines rather than imagining idealized modern cranes. Optimized designs would favor modular rigging and redundant systems enabling rapid repair, lowering overall timber consumption while maintaining lifting capacity across extended campaigns and durability. Comparative evidence from nearby cultures reveals that mechanical concepts circulated in antiquity well before classical descriptions of complex lifting devices. Levantine and Mesopotamian workshops show early use of levers, wheeled transport, and composite tools that imply an experimental mechanical mindset. Technology transfer along trade routes and through diplomatic exchange could seed ideas adapted to local raw materials and social structures in Egypt. Such diffusion helps explain how mechanical thinking might have evolved incrementally, with local artisans solving specific problems and sharing successful patterns. The possibility of cultural transmission softens the idea that ancient Egyptian machines arose in an isolated flash of genius and makes them part of a longer arc of technological practice. This gradual adaptation aligns with archaeological glimpses of incremental innovation visible in distributed toolkits and workshop remnants. Experimental archaeology provides the most direct test of mechanical hypotheses, translating conceptual rigs into physical reconstructions that either succeed or fail under realistic loads. When teams build wooden gantries, jibs, and counterweight systems using period-appropriate materials, results show clear reductions in required manpower for lifting tasks and improved placement control. These trials also expose durability limits and the cumulative resource costs of extended campaigns, which inform models of sustainability. Repeated experiments under varying conditions can refine design expectations and suggest operational rhythms for maintenance and replacement of consumables. Overall, the experimental record validates the mechanical approach as plausible and instrumentally useful, even as it highlights trade-offs. Measured experiments demonstrate not only mechanical feasibility but also practical constraints, prompting refined models that integrate reliability, consumable rates, and workforce scheduling over decades. Skeptics caution that absence of direct machine artifacts makes the hypothesis provisional, and they demand stronger archaeological corroboration. The most forceful rebuttal remains the notion that human organization alone can account for achievement given sustained administrative will, abundant seasonal labor, and practical ingenuity. Yet demanding airtight proof can blind researchers to indirect signatures that mechanics leave behind, especially if the devices were ephemeral or intentionally salvaged after use. The methodological challenge is to develop criteria that can discriminate between pure manual methods and mechanically assisted ones, focusing on patterns of wear, mounting evidence, and spatial distributions of features. Robust methodological frameworks help researchers frame falsifiable predictions, and new technologies like ground-penetrating radar, residue analysis, and micro-wear studies enhance the search for indirect machine signatures in ways unavailable to earlier generations. Methodical skepticism protects scholarship, while targeted fieldwork guided by experimental predictions can reveal subtle wear patterns and mounting traces that confirm mechanical assistance beyond reasonable doubt and evidence. If lost machines did play a key role, then the architectural sophistication might reflect a deeper knowledge base, one that fused material science, geometric theory, and practical mechanics. That idea invites speculation about earlier traditions of engineering, perhaps a lineage of learned practice passed down and refined over generations. Could these skills have roots in even older, less documented societies that experimented with stone and timber at scale? The notion of rediscovered or inherited knowledge complicates linear narratives of technological progress because it suggests cycles of innovation and loss rather than steady accumulation. Such cycles could produce peaks of extraordinary capability followed by intervals where key techniques vanish from collective memory. If such inheritances existed, they would challenge linear narratives and suggest cycles of technological ascendancy interrupted by social collapse or cultural shifts. Standing before the pyramid with this evidence in mind, the question becomes urgent and unsettling. Are these monuments the last visible remains of an engineering tradition whose most crucial tools have been quietly erased? The signs of precise workmanship, calibration, and material logic point to an organized technical culture capable of devising temporary machines that solved real mechanical problems. At the same time, the fragmentary nature of remains, the resource constraints, and the socio-cultural patterns of secrecy render definitive proof elusive. The lost machine theory thus remains both promising and provisional, a research program that reorients field questions and invites new experiments. Facing the pyramid with these considerations in mind, the lost machine hypothesis reframes the monument as an artifact of applied mechanical reasoning, and it provokes a search for evidence in unexpected seams and shadowed corners that conventional models had not prioritized. Chapter 5, Theory 2, the Sound and Vibration Hypothesis. Dawn over the plateau hushes the air and opens a space for a strange idea to take hold. Picture a small team of craftsmen and ritual specialists gathered near a newly quarried block, holders of horns, drums, and taut membranes. The image reads like ceremony, but in many ancient societies, ritual and technique braided closely together. If vibration can alter friction or reorganize granular packing, then a chant or a tuned horn might be more than symbolic speech. The suggestion pushes modern sensibilities because it asks us to imagine sound used deliberately as a mechanical agent rather than only as a sign. This chapter explores what that could mean, what sorts of instruments might have been plausible with available materials, and how songs or tonal devices could be integrated into large-scale coordinated labor. It asks us to listen to the stone, to treat legend as potential clue to method, and to open experiments that probe sound as tool and evidence. Ancient texts and later liturgical fragments sometimes describe instruments and pitched sound in contexts that blur ritual with efficacy. Temple inscriptions and hymn fragments praise the power of speech, horn blasts, and rhythmic percussion in creating order and shaping worlds. Language here is often metaphorical and layered, yet the repetition of sound imagery across time suggests a cultural conviction about sonic agency. Priests trained in tonal performance might double as technicians who knew how to sustain pitches and rhythms. Musical iconography in tombs and temples shows a wide variety of wind instruments and percussion, and these instruments could be adapted to work. Mythic accounts that frame divine speech as causative resonate with an ontology where vibration carries force. Taken seriously as applied knowledge, such motifs invite experimental translation into devices and procedures. They also offer a social explanation for secrecy, because ritual procedure and technical know-how could be effectively guarded within cultic lineages for generations. Modern experiments show that sound can alter material behavior in measurable ways, providing plausibility to acoustic ideas when translated carefully into engineering terms. Standing waves can trap particles and droplets, while ultrasonic fields can lift or suspend small objects in laboratory settings. Resonant amplification concentrates energy in specific zones and can change how granular beds and thin films behave. Laboratory rigs demonstrate reduced drag on sliding test blocks when vibration is applied, and researchers have observed wave-driven fluidization of sand that allows heavier items to move more easily. These findings do not prove large-scale lifting of multi-ton stones, but they do identify physical mechanisms that reduce static friction and aid incremental motion. Understanding how to couple acoustic energy efficiently into stone and substrate is the crucial engineering challenge rather than a metaphysical leap. The experiments provide a testable framework and invite scaled field trials designed to respect archaeological constraints and realistic materials. Energy budgets must be measured and reported openly. Consider engineering mechanisms by which vibration could assist movement in practical terms. Vibration can fluidize granular materials by loosening particle contacts and reducing internal friction, allowing sand to behave more like a mobile substrate. Resonant excitation of contact surfaces introduces micromotion at interfaces, converting static friction into dynamic friction and lowering the force needed to start sliding. At the scale of heavy blocks, tiny relative motions at contact points can accumulate into measurable shifts when applied rhythmically and directed. Coupling vibration into the base of a sled or into the sand beneath it could momentarily reduce drag and ease hauling, cutting human effort and equipment strain. If resonant modes are excited within a block or its bedding, focused vibration might free a tightly seated stone with less brute force. Transmitting energy efficiently into these modes remains the chief technical obstacle and invites inventive solutions like resonant chambers and diaphragms that concentrate acoustic power and careful measurement of energy transfer. If builders intended to harness acoustic effects, they would require instruments and structures that amplify and focus sound energy reliably. Large resonant cavities like stone chambers or assembled timber boxes could concentrate vibrations and couple them into nearby blocks or sand beds. Horns, trumpets, and conical tubes focus acoustic energy directionally, while stretched membranes and drums produce deep low frequencies with substantial displacement. Simple reed instruments or sliding flutes could supply repeatable pitches that teams could tune through trial and practice. Constructing a resonant frame is within the competence of skilled carpenters and masons. A wooden enclosure with diaphragms and resonant openings can magnify pressure changes and direct them into adjacent media. Materials matter because wood and treated skins vibrate differently than stone. Combining media could create constructive interference that enhances specific modes. Consistency of pitch and timing requires trained operators, and that social architecture fits with ritual specialization and guilds who might preserve acoustic protocols across projects and endurance. Archaeological signatures of acoustic technology would be subtle and pattern-based rather than striking like metal gears. Researchers might find aligned cavities or pits placed to function as resonant nodes, terraces shaped to reflect or focus sound, or deliberate hollows in stone that act as bellows, where patterns on sled routes and launching points could indicate repeated percussive excitation rather than only steady dragging. Organic residues such as tar, resin, or treated skins in strategic locations might mark the presence of diaphragms or membranes used to generate sound. Distribution of instrument fragments near work sites rather than purely ceremonial spaces could suggest dual use in ritual and construction. Acoustic interventions could leave microfracture patterns embedding stones consistent with repeated vibratory loading, detectable through microstructural studies. Acoustic mapping and residue studies could reveal patterns. Skepticism is warranted because the acoustic hypothesis faces steep energetic and technical hurdles that cannot be ignored. Moving multi-ton blocks with sound would require enormous energy if attempted by direct levitation, and coherent vibration attenuates rapidly in complex media like sand, rubble, and heterogeneous stone. Transmitting enough energy to alter friction over broad contact areas across tens of meters challenges any plausible period instrument, and maintaining phase coherence across distributed teams compounds the problem. Direct archaeological evidence for apparatus designed to generate high-power acoustic fields is scant, and perishable materials that might have performed these functions rarely survive millennia. Critics therefore argue that acoustic ideas drift toward fantastical thinking without practical substantiation, and they demand rigorous energy budgets and reproducible field results before accepting large-scale claims. These objections are serious and shape how test protocols must be designed, insisting on clear mechanistic models, transparent data, and scaled trials that confront energetic realities under conditions faithful to the period explicitly. Controlled experiments have probed vibration and granular media with results that are intriguing but not decisive for monumental construction. Laboratory rigs that apply oscillatory forces to sand beds show fluidization thresholds where drag on test sliders drops significantly under specific frequencies and amplitudes. Field pilots that attach vibratory motors to sleds demonstrate momentary reductions in pull force over distances, hinting that vibration can assist under favorable conditions. Most trials operate at small scale, using modern power supplies and drivers rather than period-accurate horns or membranes, so translating results to historical contexts remains speculative. Yet these experiments chart important parameters: frequency ranges that affect granular packing, amplitude thresholds for fluidization, and coupling geometries that maximize energy transfer. They also reveal failure modes, including rapid energy dissipation, heating of materials, and uneven effects across heterogeneous substrates, which any theory must address. Refined trials using historically plausible instruments and careful measurement protocols are the next step toward testing acoustic utility in the field. If acoustic practice existed, its social expression might explain why technical detail hides within ceremonial language rather than explicit manuals. Ritual music can serve multiple functions simultaneously. It coordinates labor, encodes timing, and legitimates actions while also producing physical effects if tuned properly. Songs and rhythmic patterns can synchronize teams, aligning pulls and pushes to amplify net force and reduce shock loads. And in acoustic regimes, those rhythms might also match resonant modes in instruments or substrate. Priests and master craftsmen working together could direct both symbolic performance and practical operation, making sacred ritual the face of otherwise technical protocols. This layering preserves knowledge within religious structures while mobilizing communal labor with cultural meaning. Encoded instruction through chants and gestures makes training reproducible without producing durable written treatises that could circulate beyond tightly defined guilds. Such social arrangements would make acoustic practice both a working technology and a performative institution, hard to separate into neat categories of sacred or profane. Fragments of lore across distant cultures hint at sound used for extraordinary effects, and such parallels make the acoustic idea more plausible. Tibetan tales speak of monks using horns and chants to assist in moving stones, emphasizing trained technique and control. In Mesoamerica, ritual sound accompanies foundational rites and construction songs, while Near Eastern myths link divine speech to cosmic ordering. These echoes may preserve technical kernels embedded within ceremonial language, where practitioners adapted acoustic phenomena to practical ends. Shared motifs do not prove a single global technology, but they reveal recurrent human strategies, encoding technique in ritual and coordinating labor through sound. When these patterns align with physical traces and feasible transmission routes, they merit comparative study rather than dismissal as coincidence. Ideas could spread via trade and itinerant craftsmen, creating local variants adapted to materials. Regional adaptations reflect local ingenuity. If acoustic methods were applied, they would most plausibly serve targeted roles rather than replacing all mechanical systems, shaping operation at multiple stages. For example, vibration might reduce friction during initial hauling, aid in fine adjustment during placement, or help free stones trapped in tight seats where brute force risks damage. Such uses minimize energy demands relative to wholesale levitation, focusing acoustic input where it offers high leverage on specific frictional interfaces. A hybrid model thus seems sensible. Human labor, simple machines, and acoustic intervention combine to lower peak loads. Acoustic practice could complement counterweights and jacks by smoothing transitions and reducing the shock of motion, prolonging equipment life and lowering logistic costs. This hybrid approach aligns with archaeological evidence that shows both large organized labor forces and specialized skilled crews, allowing each component to contribute where it is most effective. In this framing, sound is a facilitator rather than a miracle, a subtle tool that augments long-standing craft traditions modestly. By chapter's end, the acoustic hypothesis stands as one of the most provocative alternatives to purely mechanical explanations, and it insists on different questions. It reframes ancient builders as empirical practitioners who might have explored physical phenomena experimentally and encoded findings in ritual form. The theory draws support from mythic echoes, laboratory analogs, and preliminary field trials. Yet it faces hard limits in energy scaling and archaeological visibility. Resolving these uncertainties requires rigorous experimental archaeology that couples acoustic physics with realistic materials, historically plausible instruments, and careful measurement of energy transfer and mechanical effects. Field trials must use period-appropriate materials and replicate environmental conditions to test whether vibratory methods offer useful reductions in effort or improve control during placement. Such research should be transparent, reproducible, and interdisciplinary, pairing physicists, engineers, and archaeologists. If acoustic methods prove useful in scaled trials, they would reshape our understanding of ancient technical repertoires and alter how we read ritual sources as potential technical archives. Chapter 6: Echoes of Lost Knowledge in Global Myths. Across oceans and centuries, similar motifs whisper in different tongues, patterns that suggest more than coincidence and invite serious comparison. Imagine a Tibetan plateau chant that accompanies the hauling of a ritual stone, a Mesoamerican flute that sounds the start of a foundation rite, a Mesopotamian hymn that frames the king as architect of ordered cosmos. These scenes are not identical, yet they share a logic. Sound organizes human bodies, marks time, and encodes procedures. In societies where literacy is rare and craft knowledge moves in embodied practice, sonic protocols serve as reliable transfer techniques. Rhythmic cadence preserves timing, and pitched signals coordinate distributed teams across noisy landscapes. When researchers find repeated motifs in art, song, and ritual across distant regions, the pattern deserves inquiry rather than dismissal. Comparative study does not equal proof, but it lights paths for targeted experiments and focused archaeological searches. The evidence invites further study and careful experimental testing. Tibetan accounts contain some of the most remarkable narratives linking sound to physical manipulation, and while legend and embellishment complicate literal readings, the repetition of motifs demands careful treatment. Monastic tales describe horn blasts and throat singing that seem to alter the behavior of objects, assisting in moving heavy stones during sacred construction. Ethnographic records of Himalayan builders show sophisticated use of signals, tones, and instruments to coordinate labor in precarious terrain where sightlines fail. Long, low-frequency horns and ritual drums carry across ravines and can align teams on remote slopes, enabling complex lifts and carries that would otherwise be chaotic. Instruments tuned to resonate with local materials could create predictable responses in sand, soil, and wooden platforms. These traditions preserve empirical knowledge embedded in ritual forms, knowledge that is repeatable and teachable across generations. The evidence invites further study and careful experimental testing. In Mesoamerica, the construction of monumental stone complexes also entwine sound, ceremony, and labor, and pictorial codices and iconography preserve scenes of musicians and processions intimately tied to foundational rites. Trumpets and shell horns appear in ritual assemblages accompanying cornerstone ceremonies, and rhythmic drumming supports synchronized movement in community labor when large objects must be shifted. Building songs that coordinate time and motion transform collective effort into a finely tuned operation, where pulls and heaves become musical phrases that reduce injury and distribute load. The acoustic ecology of plazas and causeways enhances the utility of sound as both coordination and potential mechanical aid, and ritual specialists who direct these performances gain technical authority. Ethnographers note that in some traditions the sound itself is treated as a causal agent, a belief that may reflect experience of its operational effects. The evidence invites further study and careful experimental testing. Mesopotamian sources complicate the picture with cosmological language that frames creation as an act of ordered sound, where the king or priest speaks the world into being and binds chaos through ritual utterance. Hymnic traditions that equate speech with causation may encode operational knowledge in poetic guise, using metaphors that hide practical instruction in sacred narratives. Craftsmen and temple personnel often worked side by side, and rituals that structured labor likely contained procedural components disguised as invocations, making guild practice legible only to initiates. If practical knowledge rode on the metaphorical language of myth, it would explain why technical detail is scarce in public archives, yet present in the embedded practice of temple construction. Such encoded instruction may have aided transmission while protecting secrets within ritual hierarchies, aligning social control with practical advantage. The evidence invites further study and careful experimental testing. Beyond these specific traditions, a web of comparative data suggests that cultures developed analogous methods for solving similar mechanical problems under different ecological constraints. Where timber was scarce and rope expensive, societies emphasized coordination and timing, using human rhythm to multiply effective force. In mountain or jungle environments where visibility was poor and terrain uneven, acoustic signaling provided reliable coordination across distance and complex sites. When engineers lack abundant consumables, they turn to social technologies, song, chant, and percussion that scale at minimal material cost. Convergent evolution of such practices across separate regions points to common solutions for common constraints rather than mysterious diffusion alone. Identifying these shared logics reframes myths as ethnographic evidence and points engineers toward experimentally tractable hypotheses about sound aiding construction. The evidence invites further study and careful experimental testing. Linguistic patterns add weight to the argument because many languages use the same terms for ritual utterance and technical instruction, suggesting an overlap in conceptual domains. A word that in one register names a construction chant may in another function as a term for coordinated labor or timing cue. Such semantic layering preserves knowledge while granting it social authority, embedding instruction in forms that resist casual misappropriation. The oral transmission of craft often uses mnemonic devices, cadenced recitation, and melodic patterns to preserve sequences and timing that would otherwise require written manuals. These mnemonic and performative aspects make sound an efficient medium for passing intricate procedures across apprenticeships and long distances. Scholars who ignore the linguistic dimension risk missing where technical instruction hides beneath ceremonious phrasing and metaphor. The evidence invites further study and careful experimental testing. Comparative ethnography offers living analogs that illuminate how ritual, sound, and labor intertwine in practice. In many contemporary traditional societies, community projects such as house building and corvée labor still rely on musical cadence to time pulls and lifts, and long-range horns synchronize workers across fields and rivers. Anthropologists document cases where low-frequency percussion reduces perceived effort and mitigates jerky motion during hauling, while melody and chant preserve shift patterns and maintain morale during repetitive strain. Modern trials with coordinated chants show improved efficiency in group tasks, demonstrating the pragmatic value of sonic coordination even apart from any direct mechanical effect on materials. Ethnographic continuity suggests that ancient practices might operate under similar principles, meaning that ritual performance offers both social and mechanical benefits that are historically plausible. The evidence invites further study and careful experimental testing. Transmission routes for acoustic ideas may have been social and commercial as well as ritual, moving along trade networks, artisan itineraries, and religious pilgrimages that connected distant workshops. Musicians travel, craftsmen migrate, and religious specialists carry liturgies across borders, blending local practice with adopted technique. Ports, market towns, and temple centers serve as nodes where knowledge aggregates and diffuses, and acoustic practices with demonstrable utility would disseminate through these networks. Where a technique proves effective in one environment, merchants and itinerant artisans could adapt elements to local materials, generating regional variants that preserve core principles while changing form. This networked diffusion explains how similar sonic practices arise in distant places without requiring single-source origin stories. The evidence invites further study and careful experimental testing. Material traces of acoustic practice are faint but recoverable with targeted methods that archaeologists are only beginning to deploy. Microstratigraphic analysis can detect repeated percussive loading, and residue studies identify organic remnants of skins and adhesives that might form part of resonant diaphragms. Geoacoustic modeling of sites can reveal likely resonant nodes in architectural layouts and allow researchers to test how sound would propagate through specific material assemblages. Where hollows, cavities, or aligned terraces appear in contexts associated with building activities, they warrant acoustic mapping and experimental replication. Archaeologists who combine micro studies with acoustic simulation can narrow down plausible instrument placements and modes of operation, turning mythic language into testable site-specific hypotheses that either survive or dissolve under scrutiny. The evidence invites further study and careful experimental testing. Skeptics rightly warn against romanticizing myth as literal manual and caution that parallels may be coincidental or rhetorically shaped by later compilers. Comparative patterning can produce plausible narratives that nevertheless lack direct causative evidence, and cultural similarities may arise from common human constraints rather than shared technical knowledge. The methodological challenge is to construct falsifiable propositions, specific tests that would confirm or disprove acoustic intervention in construction contexts. That means building experiments designed to replicate environmental conditions, using period-appropriate materials, and measuring energy transfer and mechanical effects precisely. Only rigorous, repeatable results can move the acoustic hypothesis from intriguing possibility to credible theory, and skepticism plays a vital role in sharpening test design and guarding against wishful interpretation of ambiguous traces. The evidence invites further study and careful experimental testing. If a network of acoustic techniques did circulate and adapt, the implication for how we read ancient sources is profound. Ritual description and myth become potential repositories of technical data, and the historian must learn to hear instruction beneath invocation. This reorientation demands humility and interdisciplinary collaboration, pairing linguistic analysis with experimental physics and archaeological excavation. It requires scholars to accept that purposeful technical information may hide in metaphor, and that sonic ritual can function as both social technology and applied mechanics. Opening this interpretive channel could reveal a distributed tradition of sonic engineering that complements mechanical devices and human labor, altering how we reconstruct ancient projects and assign credit for innovation. The evidence invites further study and careful experimental testing. As the chapter closes, the echo of global myths reframes the pyramid not as an isolated marvel, but as part of a wider human experiment in solving hard mechanical problems with available resources. Across time and place, humans devised clever strategies to synchronize labor, optimize force, and manage risk, and sound proves an elegant, low-cost technology for doing that work. Whether acoustic practices in Egypt involved only coordination or also included direct physical modulation of friction and packing remains unresolved, but the comparative record shows that the question is plausible and worth pursuing. The next chapter will weigh the final implications and ask if the great stones guard not only secrets of technique, but also clues to how knowledge travels, hides, and sometimes returns to the light. The evidence invites further study and careful experimental testing. Chapter 7: The Final Revelation Between Science and the Impossible. Standing at the base of the Great Pyramid, the mind balances wonder with method and seeks a verdict that remains unsettled. Two bold hypotheses have been tested against architecture, archaeology, experiment, and imagination. The lost machine idea translates anomalies into engineered solutions, proposing temporary cranes, gantries, counterweights, and jigs that increase mechanical advantage. This account fits signs of precise joinery, repetitive sockets, and specialized workshops able to tend complex rigs across seasons. It reduces the need for massive ramps but requires sustained timber rope and maintenance regimes that leave few durable traces. The acoustic hypothesis asks whether sound resonance, vibration, and rhythmic coordination served as practical tools to reduce friction, fluidize granular beds, and synchronize labor. It aligns with ritual sources, ethnographic parallels, and laboratory findings about vibration effects on granular media, yet faces steep energetic and coupling obstacles when scaled to multi-ton blocks. Both theories are not mutually exclusive and may operate together in complex sequences across time. Archaeology provides the empirical core of debate, yet it rarely speaks in absolute terms. Material traces such as mortise sockets, grooved bearings, and repetitive hole patterns offer indirect hints of mechanical assemblies, but lack single decisive artifacts like brass pulleys preserved in situ. Experimental archaeology has reconstructed plausible rigs demonstrating staged lifts, counterweight hoists, and portable cranes that lower peak manpower and increase placement control. Those trials show feasibility and highlight maintenance and consumable demands that impact logistics over decades of construction. Similarly, controlled vibration experiments show reductions in sliding resistance under certain frequency and amplitude regimes, but rely on modern power sources or compact motors to produce consistent energy. Translating small-scale laboratory successes into historically plausible acoustic systems requires bridging energetic gaps and demonstrating coupling efficiency using period materials. Both fields therefore nudge toward hybrid models, but also demand rigorous falsifiable predictions that fieldwork can seek through targeted surveys, micro-ware analysis and residue testing, and reproducible experiments. A compelling way forward recognizes that multiple techniques could operate in concert rather than in competition. Hybrid models imagine organized manpower supported by simple mechanical devices and occasional sonic assistance to lower peak forces and increase control. Under such arrangements, general crews handle hauling over distances, while specialist teams deploy temporary cranes, jacks, and counterweights at critical moments to ease final placement. At the same time, trained operators might coordinate timing using tuned calls, drums, or horns to synchronize pulls and regulate the rhythm of effort across distributed teams. This choreography conserves scarce materials by concentrating heavy-duty timber in reusable rigs and reduces cumulative error through measurement and jigs. Social evidence for differentiated roles training and provisioning in worker settlements aligns with this model and suggests knowledge withheld inside guilds rather than broadcast publicly. Hybrid accounts therefore produce concrete archaeological expectations about clustered where mounting sockets and planned hollows that can be tested experimentally and in the field. Scientific inquiry requires bold ideas to face empirical tests with clear criteria and reproducible methods. To weigh lost machines' acoustic assistance or hybrid explanations, researchers must design experiments that respect environmental constraints, resource availability, and material behavior plausibly accessible to ancient builders. Using historically plausible materials or calibrated analogs, they must measure energy budgets where rates and throughput across extended cycles rather than rely on single demonstrations. Teams of engineers, physicists, archaeologists, experimental craftsmen, and ethnographers can translate mythic phrasing into operational hypotheses and then measure outcomes transparently. Tools like ground-penetrating radar micro, where studies residue chemistry, and acoustic simulation enhance field inquiry and can reveal subtle signatures that older surveys missed. Ethical practice mandates avoiding harm to irreplaceable monuments, so tests should use scaled analogs, controlled testbeds, and collaboration with local authorities to ensure cultural respect. Only rigorous interdisciplinary protocols can produce falsifiable results that move debate beyond speculation. Funding and public engagement will determine research feasibility urgently. Beyond empirical tests, the debate forces philosophical questions about knowledge transmission and loss across millennia. If mechanical rigs or acoustic protocols once existed and then vanished, we face historical cycles where advanced practice can disappear with social collapse, shifting priorities, or deliberate secrecy. That prospect unsettles teleological narratives of linear progress and suggests that technological peaks may ebb and flow within human societies. Loss of technique might occur through changing institution, loss of trade routes, or suppression of guild knowledge in political shifts, leaving monuments as orphan testimonies to abilities no longer widely known. Accepting this possibility imposes humility on modern scholars who assume that surviving documentation equals comprehensive understanding of past capabilities. It also reframes monuments as complex palimpsests where visible stonework encodes layers of technique, ritual, and social organization that demand careful decoding. Such reflection reminds us that recovering ancient technique is not merely academic, but a reckoning with how fragile complex knowledge can be across generations indeed. Extraordinary claims require extraordinary evidence, and that maxim applies squarely to suggestions of acoustical levitation or disappearing advanced machines. Credible acceptance demands convergent evidence from multiple independent lines, archaeological signatures, experimental replication, and clear mechanistic explanations that bridge theory and material reality. Energy budgets must be articulated, reproducible trials must demonstrate gains under period plausible conditions, and archaeological surveys must locate supporting contexts such as mounting residues, aligned cavities, or clustered wear. Historical linguistics and ethnographic parallels can bolster plausibility but cannot substitute for physical corroboration. Scholarly standards also require transparent publication, data sharing, and peer review, so results are subjected to critique and independent reproduction. This process protects against wishful interpretation and ensures that dramatic claims either survive scrutiny or are rightfully discarded. Researchers should set benchmark experiments with clear success criteria and publish negative results as well too. If either lost machines or acoustic techniques played material roles in pyramid construction, the historical stakes are high because narratives of human progress and ingenuity would need recalibration. A confirmed mechanical tradition lost to time would highlight pre-modern engineering sophistication and invite reassessment of how craft knowledge circulated across ancient networks. If acoustic methods prove effective, their discovery would broaden the range of plausible human technologies and show that experimentation with physical phenomena occurred in ritual contexts as much as in workshops. Either outcome would reshape our appreciation for the diversity of human problem solving and challenge assumptions that link modernity exclusively with technical mastery. The findings would also transform museum interpretation, pedagogy, and public imagination by adding nuance to stories of labor, innovation, and secrecy. These revelations could inspire contemporary engineers to rediscover low-resource techniques with modern applications in sustainable construction and disaster response. History thus becomes not merely record but resource, as recovered knowledge informs future practice. The simplest answer may well be a complex one, blending elements of both theories rather than privileging a single sweeping explanation. practical builders likely adopted multiple strategies tailored to stage material constraints and available expertise and changed tactics as projects progressed. That flexibility means the archaeological record will preserve a mosaic of signatures, some aligning with mechanical rigs, some consistent with acoustic coordination, and many reflecting ordinary craft. Interpreting this mosaic requires patience, careful statistical sampling, and avoidance of narratives that overgeneralize from exceptional finds. Researchers must build models that accommodate heterogeneity and then test those models across sites' chronological phases and material assemblages so patterns emerge through comparison rather than assertion. This methodological humility recognizes that human ingenuity often uses layered solutions and that simple stories rarely capture layered practice. Our task is to seek patterns, not prove myths instead. Future research must be ambitious, inventive, and disciplined, pursuing field surveys, experiments, and archival work in parallel. Targeted excavations should prioritize sites likely to yield mounting residues, aligned cavities, or clustered worksite debris predicted by mechanical and acoustic models. Experimentation should scale from laboratory rigs investigating frequency coupling and granular fluidization to larger controlled trials using period-plausible materials and instruments. Teams should document energy inputs where rates and throughput while publishing full datasets so other researchers can replicate or challenge findings. Collaborative networks that include local authorities, communities, and interdisciplinary scholars will ensure cultural sensitivity, support, and methodological rigor. Funding agencies can catalyze progress by underwriting long-term programs that accept iterative negative results as informative rather than failure. Public outreach enhances support and scrutiny, and immersive museum exhibits can model experimental reconstructions responsibly for education purposes. Any investigation into the pyramids must respect the living cultures and descendant communities who steward heritage today. Monuments are not mere objects for abstract inquiry. They anchor identity, rituals, and tourism economies that matter to people now. Researchers must therefore engage communities as partners, sharing findings and inviting local knowledge that may illuminate overlooked traditions and practices. Collaborative models increase ethical legitimacy and enrich interpretation by bringing multiple perspectives to ambiguous data. Careful presentation avoids sensationalism that distorts community narratives and instead offers balanced accounts that highlight both human labor and ingenious technique. Conservators and engineers working with local stakeholders can develop experimental exhibits and controlled testbeds that educate while protecting sites. Funding research should also support local training, employment, and conservation programs that return benefits and foster stewardship and shared guardianship, long-term goals, and stability. Standing now at the threshold between evidence and imagination, we must accept provisional answers and ongoing mystery. Both lost machines and acoustic assistance offer plausible contributions to a multifaceted solution, and both invite careful testing that could transform our understanding. The most responsible stance blends skepticism, curiosity, and methodological rigor while preserving space for wonder, because monumental questions require both calculation and imagination. Embracing uncertainty invites more precise fieldwork, better experiments, and enriched public conversation about how technology and ritual intertwine. These investigations have consequences for how we teach history, who claims authority over ancient knowledge, and how the past informs present ingenuity. The pyramid thus serves as a laboratory of historical method where conflicting hypotheses sharpen techniques and where each test either prunes or fertilizes our theories. Keep exploring with care and willingness to be surprised. At last, we return to the pyramid and the choices that shaped it. The pyramids test what counts as explanation and who guards knowledge about great projects. After surveying labor models, mechanical reconstructions, acoustic experiments, and comparative myth, the historian faces a narrow corridor between plausible technique and persistent enigma. Every new test that succeeds reduces mystery, while every stubborn anomaly shows how much remains unread in stone. We should expect discoveries to arrive as fragments demanding patient assembly rather than cinematic proclamations. The final chapters of this inquiry will be written by teams that combine technical competence, rigorous field methods, and humility before the past. This possibility should inspire rigorous research, respectful dialogue, and creative public interpretation that honors evidence and local stewardship. And still there is a last image that resists technical settling and returns us to a more unsettling thought. Maybe the last block of the pyramid was never stone, but knowledge deliberately hidden from the world.